welcome to this video. In here I'm going to go over regression, which basically the Unit 2 stuff. And this is our second review session for AP Stats Final Review. And remember, for all of the knowledge point that I'm gonna talk about in this video, I have this separate single videos for each of those in my playlist. So also feel free to check them out. And this video will not be so long. The reason that I'm making those videos is just want to touch points on every details or parts of this unit, but it won't be too long, so this is not a video that I'm going to reteach you everything again. This is just a final summary video for Unit 2 and basically regression. So let's jump right in. Graphical design of bivariate quantitative data. So we're using scatterplot a lot. So what does scatterplot contains? Well, whenever you're describing scatterplot, you will be able to use direction, form, strength, and context. Context is pretty important. You have to make sure that your paragraph actually contains the details, at the same time put them into the context of the problem. Correlation and linearity. So correlation, also known as R, measure of how linear data are. And R can be between -1 to 1, and it can be equal to -1 and 1. So remember, when R equal to 1, that means the data are completely linear, and at the same time, when R is equal to -1, that means the data are completely nonlinear. So don't confuse yourself. If R equal to -1, then the data are completely like the data have no correlation. That is not the case. That just means that the correlation is not linear. LSRL, this is like the linear formula, like the linear equation that we're using since first grade, not first grade, but middle school. So y hat equal to a plus bx. So the reason I'm using y hat instead of y, meaning that we're using our predicted y values. So every examinations that we're doing right here is we are predict by using the model that we created. So we are not using actual y in here, but we're gonna use actual y when we are doing the residuals, but not here. So it contains slope, y-intercept, and predictions. So slope is b, and remember this is also the formula that on your packet, but it's not a bad idea to remember it. B is equal to r times s sub y over s sub x. So most of the cases, the question will give you those three variables and asking you to find b. And what you're going to do is just use this formula. Y-intercept, also known as a. This is also the formula on your packet, but a is equal to y bar minus b x bar. And same thing, like if the question gives you all of those variables, you can able to find a by yourself by using this formula. And remember, slope and y-intercept, those are all the predicted values. So you can see that predictions occurs a lot of times. It contains interpolation and extrapolation. So basically, we can use our prediction to help us define whether this data or the curve that we created contain interpolation or extrapolation. What does extrapolation means? Well, it means predict outside range of data set. So, for example, if the question is asking you to find a data that is far out from our range, then using the formula that we created by the prediction won't be very accurate. So it will lead to some bias or deviation from the actual y. Therefore, that's how extrapolation occurs. And same thing for interpolation, but just opposite meaning. For residuals, you're going to use actual minus predicted, which is y minus y hat. Coefficient of determination, also known as r squared. This is also every time when you're calculating a standard deviation, you're gonna first find the variant, variation of the, but the variance correspond with standard deviation, but the variation correspond with coefficient of determination, which is r squared. So this is percent of variance in y that is explained by this model. So remember, this is in y, not in x or anything else. And basically, we can say by using the model that we created, how much variance can be explained by this model for y. Take a look at outliers versus influential point. So Also, I'm gonna adding a leverage point in here, and I put all of those in here. So take a look at here. Leverage point, it means outliers in terms of x. So here is a graph. We can see that the straight linear line that fits most of the data in here are the data that we create using LSRL, but here is a point that lies outside of the range for x. Therefore, it will be considered as a leverage point. Influential point means removing it changes LSRL and R. So, for example, if we have a data like right here, then if we add to our current data, then the whole straight line, like the whole line of best fit, will be little tilted to the upper direction. Therefore, it changes the whole graph LSRL and R, the correlation of x and y. For an outlier, this is in terms of residuals. So if you have a data that is far from the actual y values, or like the data that the best fit, the line of best fit, then it will be considered as an outlier. And you will also be able to know the residuals, residual plots. How are we going to identify if it's appropriate or not? First, we have to find if it's equal numbers, both above and below x-axis, and if it's fan shape or does it have any patterns. So if all of those requirements have been met, then we can say that our residual plot fits our data, so it's appropriate. Also, be able to read a computer printout is pretty important. I have my separate videos in my playlist. Remember, it's in Unit 2. Teach you step by step how to read a computer printout, and I also have exercise for you to try, so feel free to check that out. Moving on to transformations to achieve linearity. We have exponential regression and power regression, also quadratic regression. So remember, this is the situation that I taught right here. If our LSRL does not fit to our model, like our data, then it's a good time to switch to another model. So for example, if the residual plot does not show a random pattern or does not have equal numbers of residuals on the curve, on the graph, so which means that the LSRL does not fit our data, so we can either try exponential regression or power regression. Exponential regression is x versus log y, and this is how the formula has been written as y hat equal to a times b to the x exponent. And power regression is log x versus log y, which is y hat equal to a times x to bth power. So be sure to notice the difference between these formulas. If it's exponential, then our variable is always in the exponent. If it's a power regression, then our variable is the base value, but our b value is our exponent. And quadratic regression, we don't usually use it a lot, but it's not a bad idea to familiar with this equation, which is y hat equal to a times x squared plus bx plus c. There are other transformations based on the question given to you. Also, there's situations that we need to split our data. So for example, if some portion of our data fits a LSRL, but some portion of data does not, well, we have to use separate models for this data set in order to create a line of best fit. So actually, in this case, we are going to have more than one line of best fit. So it really depends on the question. And does the model work? I forgot this part almost. So we're going to check R squared and residual plot to see if the model that we created fit our data or not. So R squared, oh sorry, I'm just trying to adjust the screen right here. So R squared is, it usually, if it's percentage, then it's from 0 to 100. If it's a decimal, then it's from 0 to 1. So we really want our R squared to be as large as possible. So if it's 99.9%, then we can put a check mark in here. Like, it means that the data is pretty fit to our model for R squared. If it's pretty low, if for example like 1%, then we maybe doubt about our data, our model that we created. Also, the residual plot, just as I said about right here, you're going to check those 3 components. Okay, so moving on to exploring categorical data. There are two-way tables, which is like here, and conditional percentage, also Simpson's paradox. So remind you about Simpson's paradox. It's basically if you have 2 groups of data, then each group has, like if you examining separately of those 2, then each of them, for example, will showing a uprising, increasing data line, like the straight line. But if you put them into a whole picture, you examining them together to see if there's a pattern of those data, then you can see that they're actually a downward direction of the curve. So that tells you a pretty fun phenomenon, which about how, like in what perspective are you examining those data will really result a different results on your conclusion. So that's how a Simpson's paradox works. And most of the cases, they won't ask you to create a Simpson's paradox by yourself. They will probably just asking you, like give you 2 ways of creating a model to find the line of best fit of our data. And if they are counterintuitive or they are opposite to each other, then that's a good hint for you to think about Simpson's paradox. And talking about that, that's all for this video. And thank you so much for watching. Again, this is just a quick review of Unit 2 regression stuff. And we're basically focusing on bivariate data in this case. Remember that Unit 1, we focused on univariate data, which is only have 1 variable, but this case, since we introduced another variable, it comes to a lot of equations and models that we can use to find our line of best fit. And again, thank you so much for watching. I hope you learned something from this video, and more content, stay tuned.